Hello, welcome to the 11th lecture in ML series. This lecture has two parts. In the first part, we will be discussing what is locally weighted linear regression and how it works. And in the second part, we will be discussing its implementation by using Python. So as we know that the linear regression gives one best line for all the data, but if the relation is not linear, one line is not enough. One of the solutions for solving those nonlinear relationship is using this locally weighted linear regression. So it gives a separate line near each prediction point by considering the nearby points. So the main point here is it constructs a new line for each prediction point. So it comes under an instance-based learning. So let us quickly recall. We had discussed this linear regression in the previous lecture, and we had defined a hypothesis as theta naught plus theta 1 x1, theta 2 x2, so on, theta n xn. And given a data set, find this theta naught, theta 1, theta 2, so on, theta n, which minimizes the mean squared error. That's what we have defined as a linear regression problem. And there an important assumption that we took is there is a linear relationship between this y and x1, x2, so on, xn. But if the relation is not linear, then one straight line is not enough. Then one way of solving is we should use polynomial features, but that polynomial features is difficult to compute, and also there is a possibility of overfitting. So the other solution is by using a locally weighted linear regression. So you consider a point and consider the nearby points, and by considering the nearby points you fit a straight line again and use that to predict that point. So that is what the locally weighted linear regression. So in case of linear regression model, as you know that we create a line for all the data by considering all the data, but here it creates a separate line for each prediction point by considering the nearby points. So how it considers nearby points is by assigning some weights to those data points. So the points which are close to the given prediction point or a given query point, the points which are closer to will get higher weights, the points which are farther gets lower weights. Now fit a linear regression model with these weighted points and use that local model for prediction. Okay, so now how are we going to define these weights? So weights, so the closer to the data point should get the points which are closer to the query point should get more weight. So, and one of the functions, one of the popular functions is Gaussian kernel function, which assigns weights by taking this exponent, and this is the xi minus xq whole square, which gives you that distance, and by 2 tau square. So tau is the one of the parameters, so which will decide how the weights should decay. For a larger tau, the weights decay slowly more points gets a significant weight, and for a small tau weight decays rapidly. That means only closer points will be considered and the remaining points will get a zero weight. Okay, so now after considering this, we will be defining our cost function. That cost function as the weighted square difference between predicted and actual values. So h theta of xi minus xi whole square, this is the square difference, and it has to be multiplied with the weight of that point. And so now we have to find this theta naught, theta 1. So here also linear relationship, theta naught plus theta 1, theta n, which minimizes j theta, we have to find. So again we can use the gradient descent. So suppose if we consider a simple linear regression, so which has only two parameters, then it will be written as theta naught plus theta 1 xi minus yi whole square into wi. So we can also use the gradient descent. So first we calculate a gradient with respect to theta naught, and similarly gradient with respect to theta 1, and we have to update the weights in the opposite direction of the gradient. So that is minus dou j by dou theta naught, and similarly minus dou j, and how much amount that has to be altered based on the learning rate, that is alpha. So by using these, and if you see that dou j by dou theta naught is, because it is x square, so it 2x square, and theta naught coefficient is 1, so you will get into 1, and theta 1 coefficient is xi, so you will get xi here. And substituting the gradient, so we will get this. So an important point is the gradient descent process is performed for each new prediction point. For each new prediction point, this theta naught and theta 1 has to be calculated. Okay, and then an alternative method that we can use, that is by using a normal equation method. That is, we can directly calculate theta as x transpose wx inverse into x transpose wy, where w is a diagonal matrix of the weights. Okay, one way is an iterative method like a gradient descent. For each prediction point you calculate theta naught theta 1, which minimizes that j theta naught theta 1. Other method is by using a normal equation. Okay, so now let us consider a simple example to understand. So as we had seen, this is a non-linear relationship. We cannot use a direct linear regression. Suppose we want to predict what is y for this x naught, which is point, then x naught, that is 4.5. For 4.5, what is the y value we have to calculate? So for that, you consider the nearby points, you give some weights to that, and all other points you give a weights as 0, near to 0. Now by using these points, fit a linear model. So let us suppose you get that linear model as this line, and by using that you can find out the value of y. So the value of y is around this minus, so it is between -1 and 0. Okay. So for each prediction point, this fits a new line by considering the nearby points. Okay. and based on the tau it will decide how many data points it has to consider, and the remaining data points will get a 0. Okay, so here there are two parameters. One is tau and another one is the learning rate. As we know how learning rate has an impact on the learning this linear model, and we will see in the implementation how tau has an impact on assigning weights to these nearby points. Okay, so when to use a locally weighted linear regression? So suppose if we have a complex nonlinear relationship, then we will be using this. But one of the disadvantages with this method is the computational cost. For every new prediction, we have to build a linear relationship, a separate line, and this is also called as a lazy learning or instance-based learning algorithm. So it does not learn a fixed global model like a linear regression. It just stores the data. And as we have seen already, that the choice of the bandwidth parameter is important. Choice of band is important. So, and we will see the choice, how to tune the choice of the bandwidth parameter in the implementation part. Okay. So, and it fits a local linear model by for each prediction based on the weighted nearby training points. Okay, but it is computationally expensive. That is one of the issues. And in the next lecture, we will see how to implement. After that, we will see what is overfitting and how to solve overfitting by using regularization technique. And also we will discuss what is bias variance trade-off in machine learning. Okay. Thank you.